I'm going to discuss today the excavation part, the part that's underground. In the engineering profession, we are very fortunate to know exactly, more or less, the characteristics of timber, of steel, of concrete. We can design them down to the come up. However, when it comes to soil, we are still learning. And experience in that domain means a lot. So if you're working with a geotechnical engineer who's doing his first or second job, you should ask for a second opinion. A little bit about myself, and I'd like to provide a small correction from what was mentioned earlier. Sean mentioned that I was the chair-elect of the ASCE Med section. I am the past chair, not the chair-elect. I graduated with a civil engineering degree from the Lebanese American University and went on to master's specialized in geotechnical engineering from Johns Hopkins. That is where I met my wife, who's also a structural engineer. I grew up in a 400-year-old stone house. It was not designated as a landmark, but one's love for old structures starts from an early age. I also enjoy old cars, and I drive one. I am on the restoration committee for the Maronite Church, which is previously the Church of the Pilgrims in Brooklyn Heights. My wife and I recently restored 2 old artist cottages in Westport, Connecticut. And I'm personally involved in numerous landmark structures around the city. So understanding excavation, what I wanted to bring to your attention is that there is a process where the entity that's proposing an excavation has to go through in order to excavate. They cannot just go in and start digging a hole into the ground. They could do that prior to 2008. However, 2008 was a defining moment. 2014 code is much more stringent. So now, if a neighbor wants to do an excavation, they have to have a design. That's a great thing if you are the neighbor, because you get the opportunity to see something on paper before it goes into the ground. So if this is an excavation that you are proposing, or if this is the excavation of the neighbor, the process is more or less the same. There has to be an investigation done first. That investigation requires doing physical probes at the site to gather data about the soil. It also requires doing some probes above ground, which are things that Don or structural engineers usually look for. But for us, we do want to understand what the soil is, where the water is, where bedrock is, what existed previously on that site. Was there a 6-story at one point and now it's 3? Was there a 2-story at one point and now it's 5? All of these play a significant role in the design of the supportive excavation down the road. So once the investigation is done, and this is required by code, a report would be issued to the client. And in the report, the geotechnical engineer includes a recommendation on what to do and a statement of what they observed at the site. Simple things. Then we move to the design. The design involves support of excavation. Support of excavation is what allows the client or the neighbor to go down for a pool, for a batting cage, for whatever they want to do at that location. And this comes to play and is very important, especially here in the city, where landmark associations and the code regulates quite well what happens above ground. You're allowed to build 60 feet high, you're not allowed to touch the facade, you have to keep these windows this way. But when it comes to underground, the sky is the limit, or China is the limit. You can go down as far as we want. The only limitation is, and there are 2, money, how much money you want to spend to go down, and not affecting the neighbors. Or we know we're going to affect them, but we want to affect them the least amount possible, while maintaining those effects within the code allowances. And then we go into construction. And that's where all hell breaks loose. Usually we do a very good job with the investigation, we do a very good job with the design. However, if construction is not monitored properly, it doesn't matter how good of a design or of an investigation one does, things could go the wrong way. And there are lots of things that lead to this. One is we do not do an investigation at every square inch of the site. The investigation is focused in particular areas. There isn't time or money or need to open the site at every location, because if we do that, we're doing the excavation. So when we go to investigate, we do few probes, representative of what we would expect. And when we go and open the ground, we find things very often that are different from what we thought was there. So that's where the construction and the monitoring of the construction comes to play. You're dealing with a competent structural engineer and a competent geotechnical engineer. Those issues during construction will be dealt with in the right way. You're not, then that's where usually 85% of the problems that happen during the construction phase, usually not related to design. And I think the closest to everyone's heart would be how to protect your building. If I may ask, is everyone here an engineer or an architect? Do you own buildings in the Upper West Side?
There are some owners here.
Some owners?
I'm an owner of a townhouse, and I was the architect and the contractor, and I was stationed 3 brownstones to the west of me, all who excavated down 20 feet, created massive water problems in adjacent neighbors. My backyard is collapsing, and there's water on the street that never goes. So I was extensively.
This is unfortunate.
Point was legal involved.
Call 5.
And this is not intended to be a lecture or anything. Feel free to interject at any time if you want to get coffee or run to the bathroom. Don't be shy. Going back to excavating 20 feet, like what you experienced next door.
One of them had a pool.
Yeah, quite common. So if you had so much problems, probably we weren't involved in that job. I can tell you that a few thousand years ago, somebody built the pyramids, and many more massive structures after that. The Romans, the Greeks, and so on and so on. We've been to the moon and back several times. So we can do 20-foot excavation underwater. We can go 30-foot underwater. It has to be designed properly and monitored properly. There is nothing that cannot be done with the right engineering. That's where we get involved. But it has to be done right. And there are risks that are sometimes not worth it. So you can go 20 feet, and if you have a neighbor that is very sensitive, maybe they're not comfortable. They're friendly, but not comfortable. So if they see a quarter inch of movement, you're gonna see a lawsuit come your way, and you may decide that that is not worth it. That doesn't mean it cannot be done. And it doesn't mean it cannot be done within code allowances. So if there is one takeaway here, is things that are designed properly can be constructed in a safe way with minimized effects to adjacent neighbors. And that's hopefully what the position that all of us would be in when we're dealing with these scenarios. My presentation is going to be a little shorter in the interest of time, so I'm going to skip through some of these things. If you have questions, feel free to interject or later, that's fine. Investigations. We have tremendous wealth of data. There are public records in the city, old maps like this 1782 map from the War Office in London. These are available in the Library of the Congress. There is a very nice collection online. It's called the Ramsey Collection. You can connect these to Google Earth, so you'll see exactly where you are to the best of the accuracy of the plans. So we start with those usually. We look at the VD map, we look at the Pleistocene deposit map, the rock contour map, and so on and so forth, to figure out what we have to deal with in the area. And then right under it, we look at our jobs that are close by. Each one of these dots is a job that we've done. For example, I zoomed into the Upper West Side areas. You see, the best knowledge is the knowledge that we have hands-on experience with. So I go look at old maps, then I go look at my database, and even if we have data from the job next door, the code still requires a geotechnical investigation. And that geotechnical investigation can take many shapes. The two most common is doing a boring, which is what you will see on the left. And that would be a machine drilling into the ground, sampling the soil comes out, an engineer classifies it, figure out exactly what it is, how strong it is. We classify, so as geotechnical engineers, we classify soils for material strength, not for environmental aspects of it. The environmental aspects are a completely different animal, which we're not going to be discussing here.
When you do those borings, what's the schedule for how many you have to do?
The 2014 New York City Building Code treats renovations in buildings as new buildings if you're changing the load by as little as 5%. So for any change on the load of the structure, for more than 5%, it's a new building. And if it is, there is a requirement for a minimum of 2 borings, up to 5,000 square feet. And then an additional boring for every 2,500 square feet after that. So a typical 20 by 100 lot is 2,000 square feet, you need 2 borings. And if the addition is less than 750 square feet, you only need 1. And this, there is a slight addition in the number of borings if this is a pile job, not a shallow foundation. They're all spelled out in Chapter 18 of the Building Code. So the borings are very important. They tell us what the soils look like at depth. So we go down to rock in many cases, and at least to a depth where all the stresses from whatever we're planning to do have completely dissipated. Because stress dissipates with depth. So for a 1 cellar excavation, which is 12 feet deep, we will take the boring at least 40. Another 30 feet, give or take, below where our footing is, at which point there is no change in stress on the soil. But what is just as important, and this is not required by code, is what you see right here, that's test pits. Test pits are not required by code. However, they tell us what the walls look like. They tell us, the pictures look much more crisp on the screen here, so I apologize for that. But from a test pit, we can tell the condition of the footing. We can tell what the footing is sitting on exactly, the width, the dimension, because that's really what we have to deal with if we're excavating in front of it. Don mentioned earlier an example where a brick wall was, or party brick wall was 8 inches thick, and suggested, rightfully so, that we shouldn't underpin half of it, we should underpin the whole thing. In reality, if we wanted to go ahead and underpin a wall, the minimum width for the underpin has to be 2 feet, because we are constructing a footing under that wall. So if the wall is 8, we have to go down and put a 2-foot thick underpin under it, then we're going to be losing some space on our side, or maybe on the neighbor's side. Maybe the wall is 8 inches thick, but it's sitting on a footing that is 2 feet. So then now we have to match the face of the footing and go down, not just the face of the wall. So these come to play, and we know this information through test pits. And if we are doing supportive excavation design, the test pits would be required. We would do test pits before we do our design.
Required by who?
Yes, yes.
Why do you think the requires?
The code deals, 1968 code had nothing about existing buildings when it comes to geotechnical investigations. So an existing building, neighbor or an owner wants to go down a cellar, or so they left it to the engineer to determine what they want. 2008 building code, they addressed it in a tangent way. 2014, it's a little more addressed. It's more defined in the structural component, in the number of borings. And this is also, it goes back to what Don mentioned earlier. Prior to 2008, the contractor didn't even have to have a design. They just went in and did what they thought is right. And most of the times it was, but there were significant times when they weren't right and things happened. So there weren't even requirements for design.
Nidal, may I interrupt just for a second? Everyone, when you're asking questions, please make sure we can hear them in the back of the room. I'm documenting the event and I can't hear your questions. Thank you.
The question was, why is there no requirement for test pits and the requirement for borings? And the answer is, the code is a living document that's being improved. We went a great way between 1968 and 2008. There was an improvement for the 2014 code, which was implemented in 2015. And There is a new version coming out. The revision duration is going to be closer to the 5-year period, not the 40-year that was in the past. So hopefully it'll be caught in the next time. So the investigation is documented in a geotechnical report. Not much is seen here, I apologize. We can go do borings, we can go do test pits, and if you're the neighbor and you ask for borings and test pits because now you know that the construction has to have them, and they give you borings and test pits, they're hiding something. There has to be a report where these borings and test pits come to in context. The engineer may say that I did borings, I found water, or I found organics, and I recommend that you do not do a shallow footing here. I recommend you go to piles, or I recommend that you do waterproofing in this area. You need to know these if you're the neighbor. Obviously, you need to know them if you're the client, if you're the owner. But if you're on the opposite side, and somebody just says, okay, here are the borings, that's not enough. You need to see a report. If they don't have one, you need to ask them for a report. And as a neighbor, you have the right to say no for anything. So you do not want the adjacent construction to affect you. Ultimately, that's the goal. You weren't looking for that construction. You don't need the noise. You don't need the vibration. You're not looking for a compensation for whatever damage. You just want to be left alone, which is your right. So you have the right to say no. However, saying no doesn't mean that the construction cannot go on. And that's where Don was trying to give his opinion, which I agree with. Sometimes it is beneficial to be part of that discussion. For example, in your case, I'm not sure how the construction transpired, but if the neighbor had provided a geotechnical report, or if you were involved maybe early on in the discussion and you had a peer review done for those drawings, there could have been a chance that some of the damages were minimized or eliminated altogether. So underpinning is one of the most common types of supportive excavation in landmark buildings. That's because we're working under existing buildings. We need to go down. We have to underpin them. If we have a party wall, both neighbors have to agree in order to underpin it. If we have independent walls, the construction site has the right to take out the walls that are on their building, with the exception of the facade, unless they get landmark approval. So they have the right to take out their own walls, and then they can temporarily support the facade in place until the new building comes in and ties into it. That happens often. But what they do not have the right to do is touch or go onto your property on either side. So if you have a building and they chose to take their wall, or even left their wall, and now they want to underpin, similar to the discussion earlier where we have a party wall and we cannot underpin half of it, if we have two independent walls sitting side by side, it is bad engineering to just underpin one wall and not the other. Because in the process of constructing the underpins, the soil under the adjacent wall will get disturbed and the wall is guaranteed to move down. So engineers recommend to underpin both walls. And it often happens that a pit is open, you go under, you underpin, then you move back and underpin the other wall. They'll be completely two independent walls. Now you have the right to say no, I don't want you to underpin my building. And this stems from the fear that underpinning will cause movement. So underpinning is, if I may rephrase, bad underpinning is associated with movement. It happens all the time. There are ways to do underpinning in a safe way, minimizing movements to within the OB limits. If there is a question on the engineering qualification or the construction qualification of the contractor, the design or the construction, then those should be brought to the neighbor's attention early on. I do not like your contractor, or I know of bad experience from other jobs. In general, if underpinning is required, it is the best course moving forward. Underpinning is usually the best way to support a building. We are constructing a new footing under an existing one, and then we are positively transferring the load from the new footing to the old, where at the end of the process, we know for sure that the new footing is taking the load. So underpinning that is done right is the best when it is necessary by design. All the other alternatives are compromises, which oftentimes result in more movement. This here, for example, is if we do not want to allow the neighbor to underpin, the neighbor has the right to step away. They're going to lose some space. They're going to put their new footing somewhere here. This slope is defined based on what we know about the soil. For example, sand will have a different slope than till, have different slope than rock, different slope than peat, etc., etc. There has to be a bench and a slope. Oftentimes, the neighbor wants to maximize the space, so this slope will go directly in front of the footing and it will be steep, maybe 1-to-1. Or even if it was flat, the excavation would be deep enough, or there would be water included in the mix, at which point there is movement that's going to result from this approach. This movement can also be addressed. So it goes back to proper design. Anytime that any of this is going on, the wall needs to be monitored, vibration and survey, and if the movement exceeds, it doesn't even have to exceed the 1/4 inch or the 1/8 of an inch. If this was landmark, the engineer has to determine that a trend is starting to develop, at which point they can do something. The wall can be shored. On a recent job where Don and I worked, the contractor had not put a shovel in the ground. For that particular job, we were both on the same side. We knew that the building was leaning, and it was landmark. We had transit authority to deal with. I advised the client that they need to brace the neighbor's building before they do anything. Don came in, designed an elaborate bracing system that supported the neighbor to minimize the risk of when we start to open up the soil. And going back to what Don mentioned earlier, anything that we do at a site constitutes a change, and a change results in movement. So they can be careful. In that case, they may have needed to brace your building before they did anything. They can do it from their side. So sometimes I would like to go a step back. It makes sense sometimes to agree to underpinning. Even though on a first look it may not sound very appealing, there is risk, but if you do agree to go into that process, you will have much more control over the outcome. You can tell them, I need the vibrations to be sent to my engineer, and I'm going to skip through slides, but all of these associated costs are typically paid for by the construction. So if you own that building, you're paying a consultant and a lawyer and an architect to review what the construction next door is doing. You have the power to have them pay for it. So it's not going to be like you're paying a lot of money out of your pocket to do that. So when it comes to design, going 2 steps back, one option is to do nothing. So we excavate down, we find that the footing is 3 feet deep, and we're only interested in increasing our cellar height by 2 feet. So in other words, we don't have to do anything. Excavate the 2 feet, we're not going under any of the footings, we're in good shape. However, if we wanted to put a swimming pool or a bathing cage or a cellar and a sub-cellar, which is often the case, then we have options, and underpinning is on top of that list. This is the best way for us as engineers to guarantee we're bracing the neighbor or the client's building, because we have positive verification that the footing is holding the new underpin is holding the old footing. All the other options that I'm listing here, and there are more that I'm not listing, are a compromise. So we can do a segmental wall, which in other words, building a stiff wall in front of the footing on the construction side. This causes a loss of space. And there is some associated movement with it, which is more than underpinning. Soil slope, we just discussed, similar effect, losing more space here. Rock excavation, by code, if the code specifies rock or divides rock into 4 classes, Class A and Class B are allowed to be used with a straight rock face cut. So if you hear that the neighbor has rock, that doesn't necessarily translate into yes, go ahead and excavate, nothing is going to happen to my building. It has to be rock Class A or Class B. If it is Class C or Class D, then you treat it just like soil. But if it is Class A or B, then we can just do a rock cut, vertical rock cut. And I have a few pictures later that I can go through. If it is rock Class C or Class D, then we introduce some reinforcing in it, which is supportive excavation. We create bolts into that rock to hold the face. And then there are other alternatives. This is a whole family of rigid walls, which includes secant walls, tangent walls, small mix walls, etc., etc. They're intended to be rigid. They're intended to carry the load from the building as the excavation advances. They do a decent job, but not good enough. You'll see those are usually associated with the most movement of the lists that I'm putting up here. Underpinning, for those of you who are not very familiar with it, we're going on, this is an existing footing right here, supporting the wall, party or not, in this case it doesn't matter. We're gonna go excavate adjacent and then tunnel underneath and go excavate under the footing and pour this new concrete footing underneath. The width of it has to be minimum 2 feet. If this footing is more than 2 feet, then the underpin has to match the footing. It could be 3 feet, it could be 4 feet, it could be 5 feet. The width of this underpin has to be minimum 2 feet, but it has to match the footing also. So we cannot take a footing that is 2 feet and make it 1. It doesn't make sense. Also, one thing is, this footing was sitting on some soil. Some could have been sand, it could have been fill, whatever. We have to always take the footing from a condition to a better condition. You cannot go from a condition to a worse condition. So we always have to guarantee. That's why I say underpinning, if done right, is always a best option moving forward. Because now we know for sure that this building that was sitting on 3-ton soil before we started is sitting on 6-ton soil when we finished. And go ahead.
So I didn't mean to interrupt, but how much movement is allowed on the adjacent structure?
For landmark buildings, very, very little. The yellow circle is the maximum movement allowed by code, which is a quarter inch. So this is how it sits on a penny, covers Lincoln's head. And then that smaller circle here, which covers his ear, that's the warning. If movements happen in excess of that, the construction has the responsibility to notify the neighbors that something is going on. Pay attention, change. If it reaches the yellow, so if it's a quarter inch, construction is supposed to stop. And this is all spelled out in the code, chapter 33, and in the TPPN 1088. Back to the TPPN 1088. So now the DOB considers the 2014 code as a replacement for TPPN. Like Don mentioned, they didn't capture every aspect of it. So you will find in, especially in historic buildings, that the engineers will reference both. The DOB wants us to just address what the code has, but we still have some issues that are not covered by the code. We refer to TPPN, and TPPN is especially useful when we are dealing with rock excavation. It doesn't really apply that much when we're dealing with soil excavation, soft stuff, but rock is where vibrations come into play, and that's where TPPN is. So back to underpinning, and underpinning has to be done in patterns. If we open under the entire wall at once, the wall will move down, guaranteed. So what we do is we open in small sections. The width of every underpin is limited to 3 feet if the footing is rubble, and is limited to 4 feet, irrespective of the condition. So no more than 4 feet opening, and this is based in great part on empirical data. Underpinning has been done for many, many years, hundreds, and when the excavation starts to exceed the 4-foot mark, the building experiences more settlement. The chances of movement increase. So in the city, it's either 3 feet or 4 feet. This is the standard. And it has to be constructed in pattern. And the patterns are in such a way such that when 2 pins are constructed, there is always a space between them that is big enough such that there is no effect in the stress. And that space is usually 12 feet. And it's a function of how deep the pin is. So if the pin is 20 feet deep, that spacing may have to be much more than 12. In general, if you're looking at 4, 5, 6 foot underpins, 12-foot spacing. So the clear distance between this A and this A is 12 feet. And what we usually do in the industry is we do it in multiples of 12. So if 12 doesn't work, it'll be 24 feet. And what this means, what you're looking at down here is the pattern. It means the contractor can have a crew constructing this pin and another crew constructing this pin at the same time. And a few things to keep in mind regarding underpinning. Time and water are both the enemy. So if we have water, underpinning may not be the best solution. Water has a lot of side effects, which I can discuss later, and time. So once we open a pit, there is something in soil which we refer to as apparent cohesion. It is this glue that temporarily holds the soil standing vertical, even though the science and our knowledge tell us that the soil has to fall to its angle of repose. This is a function of time. So we can keep the soil standing vertical for a day, maybe for an hour, maybe for 2 days, but definitely not for a month. So when we design underpinning, we require that each one of these pins is opened, inspected, steel installed, and poured in the same day. Whatever that means. It means they have to have 10 guys working on it, or one. It has to be opened and closed on the same day. Oftentimes, problems happen when this pin is open and it stays open for 3 or 4 days before it's poured. And then they're working on this one at the same time and doing 3 other things at the side, and they forget about it. The soil loses its apparent cohesion. It wants to cave in, building moves. The suspenders in doing the underpinning right is the jacking, which is what you see in these 8 pins here. Whenever a pin is bearing on soil, even with the best construction, the subgrade that the underpin sits on, which is the new footing, the new grade, gets affected during the course of the excavation. So to minimize those effects, once the pin is constructed and poured, they come on a Monday, they open this excavation down to the subgrade, they put the steel reinforcing in the pin, they pour it, and if you notice there is a portion of this pin that is above the rest here, we call this a lintel beam. This allows us to construct a smooth surface, which is often necessary, especially when we're dealing with rubble foundations up on top. Then the following day, the second day, they would come in, put a jack in here and push. And they would put in, depending on the height of the building and the soil that we're dealing with, somewhere between 50 tons to 100 tons on that one jack. The purpose of jacking is not to move the building up. The building is serving here as a weight, counterweight. The purpose is to push the pin down, And then once this jacking happens, this space here will open up more than it actually is, until such point that we start to see the slightest upward movement, which is defined by code as 1/16 of an inch, the thickness of a hair. Once we see that the building moves up a hair, we stop. And then they shim it, they wedge it, and they come and fill this void back with concrete. This is the guarantee that the pin is not going to be moving ever again down. So it would have been, at that time, experiencing much more stress than the weight of the building.
Is this detail in response to the earthquake zone that we happen to be in New York State?
Not necessarily.
So this would work for California or India?
This works anywhere. This detail is not tied to a specific earthquake zone. This is an intermediate process that allows us the confidence, provides us the confidence that the underpin is doing its job. And the jacks here are shown on the A's only. The jacks can be shown on any other combination. It's just an example. So segmental walls, this is the construction of a concrete wall in front of the neighbor. So we're losing space from our side. The appeal of this option is that the SOE, which is the temporary supportive excavation, and the permanent wall are combined into one. So we are constructing the permanent wall at the same time as the SOE, and that would be 2 foot thick. So in this scenario, the alternative would be to do an SOE, which is 1 foot thick, and then come and install a new structural wall in front of it, which takes space. There is a small savings in space when we use this approach. And if it's designed properly, the likelihood of movement with this wall are more than the likelihood of movement with underpinning, but less than all the other rigid walls that I mentioned earlier. We went through the sloped excavation. This comes at the most loss of space. Here you're spending the least amount of money because you're not doing anything here, just excavating. You're losing a lot of space, and it's not a guarantee that movement is not going to happen. And then there is rock excavation. In the Upper West Side and in the Upper East Side, rock is relatively high, so this is quite common. There are two types of rock excavations that I need you to remember if you're dealing with these kinds of issues. There is saw cutting and there is line drilling. And whenever we're dealing with rock, one or the other has to be implemented in order to minimize effect on the neighbor. Our job as engineers is not just to design. We don't go into the design intending to vibrate the neighbor unnecessarily. We don't go into the design intending to move their building unnecessarily. Our design is usually to minimize the risk on our client and on the neighbors. It's our responsibility as professional engineers to protect the public. So you will see on drawings often that the face right next to the neighbor has to be saw cut. Saw cutting, just what it means, it's a chainsaw or a circular saw that can be handheld or operated by rails attached to the face of the rock or by an excavator that will go in and smoothly cut the face of the rock. And if I was to zoom into this picture and it was good resolution, you'll find that the face of the rock is very nice. You cannot distinguish it from good concrete. And this here happens to be 1A rock. The other option is to do a line drilling. So a machine just like this one, which is sitting inside a confined space, will go and drill a hole next to a hole, next to a hole, next to a hole, right around the entire perimeter where rock is to be excavated. The idea is to create an air gap. So when they go in with a jackhammer, there is a separation, and the vibrations introduced into the rock to break it by the jackhammer are not transferred to the existing walls, into the neighbor's building. If this is not done, if saw cutting is not done, and if line drilling is not done, then anything that they do with the rock will cause the buildings to vibrate. And the human senses are much more sensitive to vibrations than the buildings, so humans will feel it right away. And then it's only a matter of time before the building, things start shaking off of shelves, paintings start falling off of walls, and things start moving. So these are necessary, very necessary. One more thing regarding rock excavation. Groundwater table wants to be at elevation 0, that's where the sea is, or elevation 5, depending on which datum you're looking at. So whenever it gets a chance, that's where it wants to be. If rock is high, which is the case in many sites in the Upper East and the Upper West, water will be flowing on the surface of the rock down to the river level. That's the way that it goes. So if we go and open up a cut into the rock, it becomes like a swimming pool. So there will have to be constant pumping of water from that rock excavation during the time that it is open. This water does not necessarily affect the adjacent neighbors negatively. It's much different than if this excavation was happening in soil under the water. If we are excavating in soil and we have to draw the water down for the excavation to happen, every foot of water that we draw down is the equivalent of adding a story onto the neighbor's building. So if we're drawing down 5 feet of water, we're adding 5 stories. The advantage, not the advantage, history is on our side in this regard, because most of those buildings have seen a fluctuation of 3 feet, which is normal rain events, water surges, etc. So if we are just playing with the water table by 3 foot, give or take, the buildings have seen those changes in the stress, and it wouldn't affect them much. But if we're going 10 feet or 20 feet or 15 feet, then there has to be a cutoff wall where we are keeping the water outside our excavation at an elevation that's not changed, and we're only pumping the water out from inside. This is what rock does for us here, just by virtue of being there. These are the alternate walls, the alternate rigid walls, secant wall or a tangent wall. They're both circles, they both have reinforcing. The difference is that here the circles are touching, here the circles are eating away at each other. So this is more watertight than this. They both serve the same purpose. Both of these are not a good idea when you're going under a neighbor. They even though they are rigid, if you read in textbooks, they say, oh, these are rigid walls, you can use them, etc., etc. They're not the best. Yes, you can use them, but you're going to be introducing movements into the ground. The construction team, your neighbor or you want to stay away from them as an owner because they're very expensive, much more expensive than underpinning. And so if you're the construction owner, that is your motivation to not do these. And if you're the neighbor, usually my recommendation to you would be if the neighbor does that, then you're going to be guaranteeing yourself movement. You're much better off allowing them to underpin. There is one other thing for underpinning that it's very rarely discussed. But if the neighbor is planning to construct a cellar and a subcellar immediately next to your building, they're going 20 feet down. By virtue of them doing the excavation, this allows you in the future to excavate down to match them with minimal supportive excavation on your side, because they've already done the work. So that is a plus that's usually hidden. If you don't want to use it now, that's fine, but you have that potential. Somebody has already done the work. Also, one more thing, when the neighbor excavates under your wall, or just exposes a wall that was buried without even going under it, it is their responsibility to waterproof their wall that's coming up and your wall in turn. So they have, for example, if they're going under the water, and there was a discussion earlier, I forgot who started it, regarding more water coming into the basement as a result of the construction, somebody's doing something wrong. There are two ways to deal with water. One way is to resist it in place. That requires constructing a watertight space under the water. We refer to it as a bathtub. Often includes installing blindside waterproofing in such a way that no water can go in. And that is a scenario where you do not have to pump. However, that's an expensive way to do waterproofing. Oftentimes when somebody's spending $15, $20 million on a pool and batting cage, they go that route. They don't want water coming in. But sometimes we're just flirting with the water table. We're very close to it. It's not going to affect us all the time, or maybe it's going to affect us, but for a month of the year. And there are alternatives that are cheaper, one of which is an underslab drainage system. That requires pumping. And it can be constant pumping, and it can be sporadic. So they can pump on a rainy day and not on a sunny day, or they can pump in the winter but not in the summer. In the past, we saw more underslab drainage systems installed than we see now. And that's because the Environmental Protection Agency is requiring permits to pump the water into sewer. If someone chooses to, spend $2,000 a year electricity to have a pump continuously running, not a big deal. It's much cheaper option than spending $500,000 on waterproofing. That's the case. So they may choose to go down the pumping route, but if the EPA is now tightening what can and what cannot be pumped, and especially if contaminants come to play, creating a bathtub is a much better option.
Will that also protect your neighbor from incursion of water, or?
That correct. So if you're doing an underslab drainage system and you're pumping the water down, you don't know where that water is coming from. So you're pumping your water and the neighbor's neighbor, wherever the water is coming from. And if you're doing a bathtub, then you're not affecting the water on the neighbor's side. You're leaving it wherever it is. Oftentimes we go into construction next to transit authority. We think that the water should be at elevation 0, but we find that the water is at elevation -10. Because the transit authority is pumping the water out because they have a leak in their tunnel and they're continuously pumping it for whatever reason, which is perfect for the construction. They spend less money on the dewatering. But that doesn't mean that design-wise we assume it's at -10. Always take it at the elevation where it will be at some point in time.
For option of rigid wall.
Yes.
If we make it really rigid, or in other words, we design that for deflections, not only for strength and stability.
Yes.
Then and on the other hand, we properly design it and construct it. Can we say that we impose the minimum disturbance to the soil below the neighbor building, and maybe a good solution from design point of view? And from economic point of view, if we consider this to be, we have the coordination with the structural engineer of the project, if we consider that as a part of the permanent foundation wall, then it will serve for two purposes, for SOE and for the permanent foundation wall. With these two considerations, can we say that it may take a better rate in those solutions?
I agree. So the question is, can we consider rigid walls as useful or as economically viable because they're doubling as supportive excavation and structural? The answer is absolutely yes. Someone can run a study to figure out how rigid can it be and still be affordable and be constructed. When we're dealing with landmarks specifically, usually we're working inside existing buildings. And that means that we have limitations on what kind of equipment we can bring in, which makes constructing something like a secant wall or a tangent wall extremely difficult. These kind of walls require machines with enough power to go into the ground and drill them, etc., etc. So these walls, even though those can double as SOE and structural, are not usually doable with the confines of a landmark building. And that's where I brought the rigid wall. The rigid wall design, we've done numerous of these walls successfully. We use them often in rear yard expansions, much more so than immediately adjacent to 6 or 5 story brownstone, because in the rear yard we have more tolerances on what movements we can expect. And they double as SOE and structural wall. You can also see, if you look here at the top, there is waterproofing behind it. So there is blindside waterproofing behind that wall. It's constructed in sections as the wall is coming to play. And this wall is constructed in vertical sections. So 1, 2, 3, one next to the other, like that. I think we're running out of time, but I'd like to jump to the conclusions. So there are many issues during construction. If you're dealing with a competent geotechnical engineer and a structural engineer, a competent design team, you will find that during construction, that engineer is at the site much more than you think they need to be. And that's not because they're doing something wrong. It's because that is when you need them to be there. You need the engineer to be at the site during construction. The design can be very good, all the T's crossed and the I's dotted. The construction is where problems happen. So you do not want to have issues like this happening in your building. If they do, they can be fixed. You just don't want to go through that experience. It's not enjoyable, and it can be avoided, which is just as important. You want to be in a position where the neighbor comes in, puts their foundation, goes out, minimal effect to you, and you want them to do it very quickly. So if somehow this can be facilitated, whatever that means, then you're gaining from it, and then you're gaining the potential of, in the future, at some point, expanding your space, which is tremendous. You don't have to put as much effort into it anymore. And we can discuss more if you like, for those who want to leave. If everything else fails, if you have an engineer that you thought was a good engineer, but they got busy, or they got sidetracked, or they got married, or they traveled, whatever, you cannot find them. You cannot find them. Just call the DOB. The DOB does not have enough staff to support everything. The way that they operate is they go sporadically to job sites, and they rely on phone calls. Somebody complains, like this squeaky wheel, it's gonna get the oil first. Someone complains, the DOB comes and visits, and they investigate. You don't want to complain too much or prematurely, because that will hurt. If you complain once, twice, 3 times, the 3rd time, oh, Joe Schmo is complaining again, we're not going. So you don't want to be in that position, but you can always call them, and they will come. Usually the excavation unit will send somebody within the hour or within a day. They will take a look, and if they agree with what you're telling them, they will stop the job until you get the opportunity to get an engineer or to review the condition. And I'd like to leave you with that.
Thank you so much. I think we do have some questions, and hopefully if people have a little time, we can stay and answer those. But does anyone have a question for either Don or Nidal? Yes.
Are there equivalents to the Veely maps for other boroughs or only Manhattan?
There are equivalent maps, not necessarily to the same detail as the Veely map, but if you go to Rumsey, R-U-M-S-E-Y, you'll find that they have a lot of historic maps, not only for New York State, but for the entire country, and some of them worldwide. It's a very good resource.
When you have a rubble wall situation and Are they required to do any additional underpinning, or is it the standard for underpinning the same for a new building or an old building?
Whenever you have a rubble wall, it means it's sitting on a rubble foundation. And what that means is there isn't much to underpin.
Right.
So with underpinning, there has to be a transfer between the new footing and the old wall, and that's where the lintel beam comes in. In one of my earlier slides, I showed two sections of the underpin and the jack in between those two sections. So there is a special detail. If this was a conventional wall that's being underpinned, then the lintel, which is the part on top, can be eliminated, and the pin will just connect to the existing footing.
Can you generalize on the cost differential standing space above ground versus below ground?
I'm not sure I understand the question.
What does it cost to add 2,000 square feet of living space in a 20 by 100 lot versus add 2,000 square feet of living?
It's much cheaper to build and upgrade holdings.
By factor of,
I would say more than 50%. In other words, it's going to be more than twice as expensive to build the same space below ground. It may not be possible, if you're in a landmark district, and so on, but no, I don't think anybody ever has as their first choice, let's excavate for that reason, but it very often ends up being what they do.
Does that factor into the FAR when you add that space?
No.
So the beauty of constructing below ground is it's free, space is free. And to put it in perspective, recent client ran the math and determined that excavating 16 feet under the water, 25 feet under street level to construct an automated parking garage within 50 feet of transit authority. So all the complications, the building is landmark and so were the neighbors, was justified based on the cost they sell the parking. So it's expensive, but you get paid for it.
What about the impact on a public street? Is obvious, can you excavate quotes freely under a sidewalk?
Nothing is free, so first it's regulated, and any excavation that happens on public sidewalk or street requires restoring the street and the sidewalk in equal or better condition than they were before. That's assuming they can get the permit to do that.
So you can excavate under
Yes.
a public sidewalk?
Yes, oftentimes the DOT will allow closing a lane, excavating part of the street. It gets complicated where you have bus stops and things of that nature, but it often happens.
We've been seeing over the last 20 years a lot of row houses converted into back to single-family houses. Because of the nature of, somebody mentioned London earlier. London sits on very soft clay. It's easy to excavate. It's difficult to have supportive excavation, but it's easy to excavate. Manhattan, it's not so easy to excavate. And London, they have what they call iceberg houses, where, most of the house is underground. We don't have that here, and we realistically cannot have that here. No matter how much money you're willing to spend, you can't do something like that because of our ground conditions. There has absolutely been a trend in the course of my career since 1987 towards single-family houses getting converted, former single-family houses that had been converted to apartments being converted back to single-family houses. I can't say I've seen a trend in terms of the excavation portion of that work.
This is actually for Nidal. In your photograph of the segmental wall, it looked like basically that was sort of, could you talk about a little bit what the shoring or the sheeting that would go on behind that? Because it looked like that was sort of a photograph of maybe where somebody was excavating right along the property line.
Correct. So this is the rear yard expansion,
Right.
82nd Street, Upper East Side, landmark. The construction, I'm going to go to the underpinning detail. So this is a typical underpinning detail when someone constructs an approach pit and they go under the footing and construct new footing, which is the underpinning. And this red line here is a tieback. Sometimes we need it if the pin is too high. If you were to assume that this wall doesn't exist, using the same concept, this is a 4-foot wide timber sheeted box. somebody can excavate. This length here can vary, it can be 10 feet, it can be 15, it can be 20. They'll go down this entire length, you have timber, so technically there is the thickness of the timber that's always going to be at the property line, it's 3 inches lost. But the wall can come and sit in here without the footing on top, and the timber stays at the property line here. And then the next section comes in, and the next section comes in.
And if there's say, a two-story slab on grade addition, where you're proposing to put the timber, I mean, this is a neighbor of mine actually is proposing to excavate 11 feet down, basically right along the property line. How would they actually do that excavation? And support, my structure.
So the best option is to underpin. That is the best approach, because this way you get the guarantee that your building now has new footing. The second best option
So
is
that would
to...
be actually on my property?
Yes.
Completely under my property?
Correct. They will go, so let's say this is the wall of the addition, they will go under the wall. So your property line would be right here in that case. And then they will construct their construction on the other side, on their side. But the next best approach is, this is your footing and the property line is right here. So then they're gonna come and your slab can be considered as a footing. And they're gonna go and construct, they're gonna be constructing this right next to your footing. So your footing is sitting here, right? So that's, there's going to be, you're gonna expect movement. So your footing in this case is here. And you want them to construct this pin on their side. And their footing doesn't exist in that case. There's nothing there yet, yeah. So you want them to construct this wall. This is the segmental wall that they're gonna construct on their side right next to your footing. That is going to result in some movement on your wall. You landmark?
No.
So if you're not landmarked, they're allowed to move your wall half an inch. Half an inch, not just Lincoln's head, the entire penny.
Hire him. Hire him for sure. Geotechnical guy.
So if they were, if I said, fine, go ahead and underpin under my slab.
Yes.
Would they do that in sections?
They will do it in sections, horizontal.
Height-wise
No,
sections?
you don't want that. You
They
want,
would do the full 11 feet.
they should. You want them to do that. You will find some designs out there that say underpinning can be underpinned. You're just adding the errors. You're multiplying the error. So you don't want that. You want them to go in and construct the underpin. There are limitations. So the deepest underpin that I've seen constructed is 24 feet. If somebody's going deeper than that, they may not be able to get it done in one day. So there's also that restriction. So 11 feet is doable, 20 feet is doable. They have 40-foot underpin, it's not doable. So something else needs to contemplate that.
We have, I'm sorry, everyone, the room is needed for something starting at 12. So we pushed ourselves here, but hopefully we can continue this conversation. We want to thank you so